Composite control modes. Continuous controller modes Part 4. Continuous controller modes. Till now, it has been discussed about following continuous controller modes: proportional control mode, integral control mode, and derivative control mode. There are control requirements that do not fit the application of any of the continuous controller modes discussed. It is both possible and expedient to combine several basic modes, thereby gaining the advantage of each mode. Proportional integral control (PI). This is a control mode that results from a combination of the proportional mode and the integral mode. The analytic expression for this control process is found from a series combination of equations 14 and 16. Request. It is hoped that this lecture is going to be useful to you. Please press like. Please subscribe. Here we are having equation 14 for the proportional mode controller. Then we are having equation 16 for integral control mode, and then by the combination of 14 and 16 we get equation 19 for proportional integral control PI, where PI naught is equal to integral term value at t equal to 0, initial value. The main advantage of proportional integral control PI mode is that the one-to-one correspondence of the proportional mode is available, and the integral mode eliminates the inherent offset. Notice that the proportional gain by design also changes the net integration mode gain, but that the integration gain through k subscript I can be independently adjusted. Recall that the proportional mode offset occurred when a load change required a new nominal controller output that could not be provided except by a fixed error from the set point. In the present mode, the integral function provides the required new controller output, thereby allowing the error to be 0 after a load change. The integral feature effectively provides a reset of the 0 error output after a load change occurs. This can be seen by the graphs of figure 18 shown in next slide. Figure 18. Proportional integral PI action showing the reset action of the integral contribution. This example is for reverse action. At time t1, a load change occurs that produces the error shown. Accommodation of the new load condition requires a new controller output. We see that the controller output is provided through a sum of proportional plus integral action that finally leaves the error at 0. Here we are having the proportional action with dotted line, and then we are having the integral action with the dotted line, and the combination of two, that is the composite action, is shown here. The proportional part is obviously just an image of the error. This is the error, and we can see that this proportional part is just an image of the error. Let us summarize the characteristics of the PI mode and equation 19. When the error is 0, the controller output is fixed at the value that the integral term had when the error went to 0. This output is given by P subscript 0 in equation 19, simply because we choose to define the time at which observation starts at t equal to 0. If the error is not 0, the proportional term contributes a correction and the integral term begins to increase or decrease the accumulated value, initially P subscript 0, depending on the sign of the error and the direct or reverse action. The integral term cannot become negative, thus it will saturate at 0 if the error and action try to drive the area to a net negative value. Proportional derivative control mode PD. A second combination of control modes has many industrial applications. It involves the serial, that is cascaded use of the proportional and derivative modes. The analytic expression for this mode is found from a combination of equations 14 and 18. Here we are having the equation 14, and then here we are having the equation 18. The combination of the two gives us equation 20, where the terms are all defined in terms given by previous equations. It is clear that this system cannot eliminate the offset of proportional controllers. It can, however, handle fast process load changes as long as the load change offset error is acceptable. An example of the operation of this mode for a hypothetical load change is shown in figure 21. Note the effect of derivative action in moving the controller output in relation to the error rate change. Here we are having the error rate change, and because of this the derivative action is like this, and then we are having the negative error rate change and the derivative action goes upwards. And then this action is due to the proportional action, and thereby the controller output has changed because of the proportional action, but at the same time we are having offset due to proportional action. 3-mode controller PID. One of the most powerful but complex controller mode operations combines the proportional, integral and derivative modes. This system can be used for virtually any process condition. The analytic expression is given in equation 21, and here is the analytic expression for PID, where all the terms have been defined earlier. This mode eliminates the offset of the proportional mode and it still provides fast response. In figure 23, the response of the 3-mode system to an error is shown. Here we are having the error, and because of this error the proportional action goes like this, the integral action goes like this, and because of this rate the derivative action gives a step output, and if we combine all 3 modes then this is the output of the composite mode. Request: it is hoped that this lecture is useful to you. Please press like. Please subscribe.